Hello, everyone. Welcome to another Science and Technology Q&A for kids and others. So I see a variety of questions here. Let me see what I can do with them. Um, well, first one, Lana says, in class, we learnt that light behaves both as a wave and a particle. How is that even possible? Okay, so there's a long history to this. People wondered what light is, and uh, starting, well, by 300 years ago, people were arguing a lot. Is light a series of little packets of light, or is light a wave, like a wave on the surface of water, but a wave somehow of something electromagnetic? They thought in some medium. Well, what happened, this is a slightly complicated story. So I guess we should think about how we observe things about light. And that's perhaps the place to start. So when light is when we're detecting light, there's the question of, are we detecting something which behaves like a particle, where it's like, boom, we just detected a particle, a photon of light, boom, we detected another photon, and so on? Or is it instead something where we're saying we're just finding the intensity of some wave that's changing continuously with time? So what happens is that there are certain kinds of things where what one detects of light is sort of the particle-like character, and there are other places where what one detects is a wave-like character. How can it be both a wave and a particle? Well, here's a way to start thinking about that isn't quite right, but it's a beginning at least. And it would be to say, well, let's what's the best way to do this? Boy, this is surprisingly tricky. Um, the um, Think about it this way. Just imagine you have lots and lots of photons, lots and lots of particles of light. Well, in together, those can, for example, have be there can be more, there can be less, and so on. So for example, when we have yeah, this is a little tricky. Um, okay, we can explain this in kind of the way the formalism works from quantum mechanics, but again, that's a little tricky. Um, Boy, this is I'm telling you, when I think one of the principles of these kinds of Q&As is that the questions that seem to me the most obvious are the ones that turn out to be the hardest to answer. And this one, let's first of all, let's talk about phenomena where what light is like as a wave, what light is like as a particle, and then we'll talk about how those two mix together. So as a wave, what's happening is that light is electric field and magnetic field, both varying rapidly. In fact, varying about 1 trillion times per second. That's what visible light has, electric fields and magnetic fields varying that quickly. And it turns out that there's a way that you can have kind of a freely propagating combination of electric and magnetic fields that wiggle that quickly, and they travel in a certain direction. So it's you are just having there's again, one of the things that confused people for a long time is that other kinds of waves exist in a medium. So, for example, a water wave, it's the water is going up and down, but there's water there, and it's the thing that's going up and down. Or a sound wave is regions of compression and rarefaction in air. There are air molecules squashed closer together. There are air molecules moved further apart. That's what sound waves are like. People sort of assumed that light waves would be the same kind of thing, that there would be this change of electric field, change of magnetic field, and that would exist in some medium. They called it the ether. And up through the end of the 19th century, that's pretty much how people assumed that light worked, that it was kind of like, instead of being compression and rarefaction of air molecules of a gas, it was kind of these distortions of this thing that was called the ether. Now, it turned out that in 1900 there was this experiment done, the Michelson-Morley experiment, which kind of demonstrated that in the most obvious way of there being an ether, just some kind of material that filled the universe, and where the Earth, for example, was moving relative to that medium, that such a thing did not exist. And so what had to be going on was that there were sort of disembodied electromagnetic fields that just existed independent of anything, just existed and moved through even a vacuum. That was the picture. It was that picture that led, for example, to relativity theory, and that was kind of trying to make consistent the idea of there is no ether, it's just disembodied electricity and magnetism that's leading to light, for example, and the characteristics of that, making that consistent with the laws of mechanics and space and time, was what led to special relativity in 1905. Well, this idea that it's sort of a disembodied electric and magnetic field, abstractly defined, that has been the dominant view of how kind of light works. It's a little more complicated than that. The idea that there isn't really a medium in which the thing exists isn't really the story in modern quantum field theory. In modern quantum field theory, there's what happens, there's kind of a constant kind of 0-point fluctuation. Everywhere in the universe, there are always kind of quantum fluctuations happening. And what's happening when you have something like light is that you have extra stuff beyond the quantum fluctuations that's made of the same stuff that makes the quantum fluctuations. In that model, it's all sort of disembodied electromagnetic field that both makes the quantum fluctuations and makes the actual light that we see. Actually, in our model of physics, now in the last few years, our physics project, things become a bit more concrete. And we actually have this kind of model of space, and we have models that we don't yet know exactly how they work, of things like photons that sort of do exist in the context of something that isn't like the ether that people imagined in the 19th century, but it is this kind of medium, this thing that makes up space, that is the thing in which things like photons exist. So we're sort of back to that same kind of idea, and we don't have to just say, oh, there's the mathematics of the electromagnetic field, and that's what determines the structure of light. It can be described in a slightly more kind of almost mechanical way. And by the way, as I mentioned, in modern fancy quantum field theory, that's effectively what's happening as well. Okay, so the idea that so this idea of sort of light as a wave is this notion of sort of disembodied electromagnetic fields varying. As I said, there's slightly more concrete versions of that show up in quantum field theory, and now even more so in our physics project. What effect does it have when light behaves like a wave? Well, one feature of waves is they can go up and they can go down. And if you have two trains of waves coming along, and you end up in a situation where the peak of one wave, of one train of waves, is sort of coming to the same place as the trough of the other train of waves, those two will cancel each other out. There'll be destructive interference of those waves. And that's a phenomenon that you see in light. You see that there can be two sources of light, and if they are producing waves that are out of phase like that, so that the peaks of one sort of are at the same places as the troughs of the other, then you will get destructive interference. An example of something related to that is the phenomenon of diffraction. So let's just talk about what these light waves are kind of like. If you have a source of light, it will be producing, well, a source of light that is sort of a carefully enough organized source of light. So a laser is an example of such a thing that produces coherent light. What will happen is there'll be a series of peaks of this of the electromagnetic field for the light, and that'll be kind of there'll be a peak, a trough, a peak, a trough, a trillion times a second or so. And that what if you have that source a long way away, what you'll find, what you'll observe is just a collection of so-called plane waves. Basically, the front of those waves, well, so if you have a point source of light, you'll have waves that come out in a sphere around that point source of light. But if you're far enough away, then you're on this kind of shell of the sphere, and at a particular place, it'll seem like it's just a flat part of the sphere, because the sphere, the place where you're looking is small compared to the radius of the sphere. And so you'll have this kind of series of wave fronts that will be kind of a plane, a series of sort of flat planes of where the electric field is largest. Okay, so what you might have happen is you've got something where you've got some light and it comes through a hole, for example. And you might think, okay, this sequence of plane waves, they get to this hole, it goes through, and wherever sort of the light wasn't blocked by the things that weren't the hole, it'll keep going, and wherever it was blocked, it won't go through. Well, there's the phenomenon of diffraction. Diffraction is that light always spreads a bit. Once it's gone through that hole, the light always spreads out to the sides. And it does that because when you're thinking about this, effectively, well, again, this is kind of complicated. The way to think about how light is moving is that one way to think about it is the light reaches some particular place, and wherever it gets to, that's a source of new light. So when light is moving through a medium, like a crystal or something, that's literally what happens. The light is absorbed by one atom, then it's re-emitted by that atom a very short time later, then it's absorbed by another atom, and that's how it moves through the crystal or whatever, is continuous, or through water or any material. It's continuously being absorbed and re-emitted. And so when it's re-emitted, the re-emission, effectively, it is re-emitted equally in all directions. And so what you get is that you're forming you can think of the light as the kind of the waves produced by the light as being formed by adding up lots of little spherical waves. And if you have lots of little spherical waves on the front of this plane wave, they'll make another plane wave. But if you're at the edge of the plane wave, if the plane wave has got stopped by kind of the edges of this hole that it's going through, at the edges of that region, you'll still have little spherical waves, but those spherical waves will end up, there'll be spherical waves that just start sending light away from the direction that corresponded to going straight through the hole. In other words, the light it'll kind of spread out around the direction it was already going in. And that's the phenomenon of diffraction. And that's a typical phenomenon that comes from the kind of wave character of light. So that's one phenomenon that goes from sort of the wave side of thinking about light. The classic phenomenon that comes from the particle side of thinking about light is the photoelectric effect, that you can have light that when you shine light on some metal or something, you can end up in a situation where a little piece of light causes an electron to get ejected. And it's like the light comes in and there's a certain amount of light and it just makes one electron. get ejected. So it's kind of like it's not half an electron because there's no notion of half an electron. It's the electron gets ejected. And so there, kind of from the particle nature of the electron, you're kind of working backwards to say, well, okay, that might seem like it's kind of a particle of light is coming in and it's making that particle of that electron be ejected. And so that's kind of the sort of particle character of light showing up in that case. And a lot of devices that we have today, the best way to think about them is a photon of light is absorbed and some electrical effect, some electron is ejected or something. That's what happens in a typical the sensor of a camera, things like this. It's again, it's a little more complicated than that, and it has to do with the way that a photon can kind of move an electron from one energy level to another. It can by absorbing the photon, the electron gets the energy that the photon had. Okay, so those are two cases. Diffraction and interference in general is a wave-like phenomenon, and things like kicking an electron out is a particle-like phenomenon. So the question is sort of how do those merge together? And the way to think about this, I think, is the way it's done in quantum mechanics is to say really what we're talking about is a kind of probability for there to be an electromagnetic effect right here. It's it's in quantum mechanics, it's usually called the wave function. And it's the thing that gives you it's not quite the probability. It's the so-called quantum amplitude, which is not quite the probability. It's kind of it gives you a kind of a quantum mechanical version of the chance that you find a piece of electromagnetic wave at this particular point. And what then one has to think about is how those probabilities kind of have a character that is like a wave. So maybe this is a way to explain it. The mathematically calculating the probability gives you something that makes the probability vary in a wave-like way. But that's just the probability. What will sort of actually happen is that there will be a particular photon that either is there or not. There's a certain probability the photon will be there, but what's actually there is either a photon or not a photon. And in fact, this is probably the best way to explain this whole story, is to think about the wave as being a sort of a wave that describes how the probability of there being a photon there varies with position and time and so on. And that's something that can be described mathematically by something that is like the waves that you see in sound waves and things like this. It's mathematically described in that way, using equations that look like the equations that are used to describe waves. But that's just probabilities. In terms of what's sort of actually there, one can better think about it as particles of light, where there's a probability of 0.2 or something. That means 1/5 of the time there'll be a particle there, and the rest of the time there won't be. So that's a first approximation, at least, is that the kind of the wave-like character is operating at the level of probabilities, and the sort of what's really there is operating at the level of individual particles. Now, unfortunately, it's not as simple as that. Unfortunately, there's it's really partly a question of whether you're just basing what you're talking about on the mathematics of the theory, or whether you're trying to kind of have a mechanical explanation of what's going on. By the time you're trying to have a mechanical explanation of what's going on, I don't think that's doable in anything other than our recent physics project. And let me see if I can give an indication of how that works Oh gosh, it's complicated. So, um, yes, let me see. I think this is going to be too complicated. I think I need to think about this offline to come up with a good, clean way to talk about this. Um, Roughly, what I will say is that in our physics project, the thing that happens that is sort of characteristic of quantum mechanics is this idea that there are many possible branches of history for the behavior of the universe. And what you end up seeing is the branching and merging of those paths, and phenomena like interference are associated with kind of things that happen in the branching and merging of those paths of history. So one that's a little bit confusing is destructive interference, when the peaks of one sort of wave kind of combine with the troughs of the other, and you get nothing there, so to speak. And what happens, I think, in our physics project is something kind of tricky, which is that the kind of paths of history corresponding to those two possibilities of the peaks and the troughs, those paths of history kind of get so separated in this thing we call branchial space that observers like us never combine them. And so for us, it's like, well, both of these possibilities just disappeared because we can't combine them together to say this is the definite thing that happened. This is complicated, and we certainly haven't worked the whole thing out. Let me just mention, in terms of waves and particles and so on, the uh, it's pretty typical that what as you change the kind of electromagnetic radiation you're talking about, that it behaves more particle-like or more wave-like. For example, in a radio wave, there are, in a sense, lots of very low energy photons associated with the radio wave. And what's most important is the kind of collective probabilities of all those photons being there or not. And that can be thought of like this wave, which has, a wavelength that might be a foot or more long. So that's at the radio end of the electromagnetic spectrum. As you go down from radio waves, you get to infrared, then you get to visible light, and then you get to ultraviolet, and then you get to X-rays, and then gamma rays. As you go down to X-rays and then gamma rays, things are behaving much more particle-like, because every individual photon is packing a whole bunch of energy. And so when that individual photon interacts with your detector or whatever it is, it does something very, very definite. It's not like a whole collection of lots and lots of photons that are doing it. It's that one photon. You can register that one photon because it's packing all that energy. In the case of radio waves, every individual photon has absolutely tiny energy. It's only the collection of many of those photons that can have an effect that you can detect with your radio antenna and so on. And in fact, one of the features of detecting radio waves is that all those photons behave what's called coherently. That is, all those photons that are in the radio wave, they're all making a little contribution, but their contributions are all adding up. And really, the only thing you get to observe with an antenna or something like that is all those added up contributions. In the case of gamma rays, for example, with that one gamma ray photon that's packing all that energy, its behavior is really quite independent of the behavior of other gamma ray photons. The interaction between those things is very small. It's kind of one photon at a time kind of thing. Whereas in the radio wave, it's the whole sort of collective probabilities that matter. Well, another thing to mention is that light, particles, photons are not the only kinds of things that have this kind of, it's a bit like a wave, it's a bit like a particle. Every kind of particle has that characteristic. Electrons, protons, all these kinds of things. But they have a certain characteristic wavelength that corresponds to kind of the scale on which their kind of wave-like behavior observed. It's called the de Broglie wavelength, spelt de Broglie wavelength. And what happens is that wavelength is, as the mass of the particle increases, that wavelength goes down. And so the higher the mass of the particle, the shorter that the wavelength over which things sort of behave in a wave-like way and show things like diffraction. So, for example, in the case of electrons, you can see electron diffraction, but it's a small effect compared to diffraction with photons because of the mass of the electron. And but all particles, all the kinds of standard particles one talks about, have this characteristic that in some sense the sort of the probabilities of where they are kind of have wave-like characteristics, whereas you can count them as one proton, two protons, three protons has a particle-like characteristic. Sorry, that was a little bit more complicated than I expected. Let's see, we have another question here from Yahoo saying, my teacher says there's no up or down in space. Why is that, and how do astronauts navigate? Well, if you're in orbit near the Earth, there is an up and down in the sense that there's a way that's going towards Earth and there's a way that's going away from Earth. But there isn't an up and down in the sense that it isn't the case that one can define down by where things fall to if you drop them. I mean, on the Earth, if you drop something, it will fall down. In orbit around the Earth, if you drop something, it won't go either up or down. It will just stay in one place. Now, why is that? Actually, it's staying in one place relative to you. You're moving in this orbit. If it's low Earth orbit, you're going at about 17,000 miles an hour. And in a sense, you are sort of falling in the gravity of the Earth. And but as you fall, by the time you've sort of fallen to the Earth, you've already gone over the side of the Earth. And so you're actually just going in this orbit around the Earth. And the whole point is that the things that are near you are also going in that orbit. And they're the acceleration that they're not they don't move towards the Earth any more or less than you move towards the Earth. And so if you put that eraser right in front of your nose and you're on the International Space Station or something, it will stay right there because it is moving relative to you. It's not moving relative to you. You're moving and it's moving, and gravity is not having the effect of gravity is there's no direct effect of gravity on that other than that it maintains both you and it in orbit around the Earth. Now, in general, gravity is produced by objects that have mass or in general energy, and the Earth is a big such thing. The sun is another big such thing. The amount of gravity produced by something decreases like the square of the distance you are from the thing. You can kind of see why that is. It's kind of like, imagine, and we were just talking about particles and waves and so on. There's yet another piece to that picture, which is fields. We talk about a gravitational field where there is an effect of gravity from a massive object. But that field is actually implemented in a sense by lots of particles streaming out, which can themselves be thought of as associated with waves. And the particles that are relevant for gravity are gravitons. And although we've never observed one directly, we kind of can think about gravity as being sort of packaged into gravitons, just as we can think about electromagnetism as being packaged into photons. And so in a sense, with any massive object, there are all these gravitons streaming out in all directions. And that's the effect of the presence of mass makes these gravitons stream out in all directions. A little bit confusingly, they're not real gravitons, they're so-called virtual gravitons, but let's put that aside for a second. Basically, they're streaming out in all directions. So if you have this ball of mass here, you've got these things streaming out in all directions. You can ask how many of them, if you are sort of if you're at a particular place away from this ball of mass, how many of these gravitons will hit you if you're just in this little region far away from this object? Well, if you think about it, they're all streaming outwards. And so the further you are away from the object, the less dense those gravitons will be. Close to the object, they'll all be there, they'll all be right there, but they're just keeping streaming out in straight lines. It's kind of like some kind of some burst coming out from the massive object. And so if you try to work out, well, how many gravitons will hit you if you have a fixed size and you're close to the object, some number. If you move further away, how many will hit you? Well, the way to think about it is in terms of the area, the surface area of a sphere. So the volume of a sphere is 4/3 pi r cubed. The surface area is 4 pi r squared, and that means that the r squared is telling you that that as a function of the radius, that surface area is proportional to r squared. And so if you're looking at a single part of that area, if you're looking at a fixed size region in that area, as that sphere gets larger, that fixed size area is a smaller fraction of the whole sphere. If the area of the whole sphere is 4 pi r squared, and you have, let's say, a size 1 region on that sphere, the fraction of the whole sphere will be 1 over 4 pi r squared. And so that's why the force of gravity, it's a way to see why the force of gravity decreases like the square of the distance, because it's kind of all these gravitons streaming out, and you are sampling one particular area, but as they stream out, they're occupying the whole area, but the area that you're sampling decreases, the fraction decreases like 1 over r squared. And so that's what happens, is that the sort of force of gravity goes down like 1 over r squared. The picture I just told you, it's not quite as simple as that in reality, but that's a rough kind of mechanical picture of what's going on. Well, that means if you're far away from all objects that are producing gravitons, producing gravity, then there just won't be any pull of gravity on you. And so and for example, if you are somewhere in space between galaxies, for example, you're far away from all the galaxies, then there really won't be much of a pull of gravity on you associated with any of those galaxies because they're just too far away. And so that's even in so that's another situation in which you just don't have any gravity sort of pulling on you. Now, there's a little bit of trickiness there because there's always a little bit of force on things associated with the expansion of the universe. In a slightly complicated way, everything is being sort of pulled outwards by the expansion of the universe. That's sort of a force a bit like gravity, but you can think of it as being a force of gravity because it's related to the curvature of space-time. But it's a sort of an additional force that's independent of there being a galaxy right there that's pulling on you. Okay, so now a question will be, well, how do you navigate how do you know which way to go if you're in space? And well, that's quite tricky because on the Earth, for example, right now, well, how do you know where to go on the Earth? You could look at the stars, and you could use something where you know where the positions of the stars are and so on. You know what time it is. That tells you where you are on the Earth. In modern times, you'd use GPS. GPS is a collection of satellites orbiting the Earth where one knows where the satellites are, and one can work out, any GPS receiver works by working out how far it is away from each satellite. So if you just have 3 satellites, you can triangulate. You can say, oh, I know I'm this distance away. You know, I'm 200 miles away from that satellite. I'm 500 miles away from that satellite. I'm 400 miles away from that satellite. And you can just sort of draw the lines and figure out, well, I must be exactly here. Well, for GPS to work, one has to know where the satellites are going to be, and one has to be able to measure that distance. The distance is measured because the satellites produce a radio signal where the radio signal is constantly changing, and the receiver knows that at this particular moment of time, the signal as sent will have been this. But because the receiver receives it later than it was sent, because it takes time for the signal to travel from the satellite to the receiver, the receiver can just work out, oh, I'm off my, I, the receiver, know that the time is exactly noon, let's say, but the signal that I'm receiving is the signal that was sent at 11:59 and some amounts of seconds or whatever, and therefore I can work out I must be this distance away from that satellite because that signal is delayed by this amount. So I can work out where I am based on those satellites. Okay, the GPS satellites are in orbit, fairly low orbit around the Earth. If you are far away from the Earth, if you're tooling off to Jupiter or something, you don't get to use the GPS satellites to find out where you are. Even if you could detect the signals from the GPS satellites, it's not really going to be good enough because all those GPS satellites are really close to the Earth. They don't give you a good way to sort of triangulate to know where you are if you're near Jupiter. So a typical thing that's been done in deep spacecraft for navigating is to use stars and to use the fact that you know in which direction you lock on to particular bright stars. For some reason, Canopus was one that was used at least in the early deep spacecraft. And as one of the, you lock onto those stars, you know those stars are in exactly these directions. And then you can again use this kind of triangulation idea to work out, well, if those stars are in exactly those directions, then either spacecraft must be right here. There are slightly fancier techniques that people have talked about. One of them is to use pulsars, rapidly rotating neutron stars that produce radio signals. And the radio signals are a bit like the GPS radio signals in the sense that they are continually, they have sort of a continual sequence of pulses. They're not as nicely distinguished as the pulses in GPS satellites, which are specially built so that essentially at every moment, you're seeing a slightly different form of radio signal, so you can tell where in the time series you are. But the idea is to use the kind of arrival time of these different pulses from pulsars as another kind of form of navigation. But it's not such an easy thing to find out where you are in deep space. And as I say, the main way you do it is by just looking at the directions of these different stars. Let's see. Wow. Okay. Well, Craig asks, is the universe as small as it is big? That's sort of an interesting question. Where are we in the scale of the universe? So we are a meter and a bit tall, roughly. The universe is 10 to the 26 meters across. So that's a 1 with 26 zeros, meters, or if I can count it down correctly, it would be a billion, can I do my arithmetic? Yeah, it's about a billion meters across the universe. And so that's how big it is. Now the question is, as you go down to greater levels of smallness, how far do you have to go down? Well, so for example, an atom is about 10 to the minus 10 meters across. So that's a 1/10 billionth of a meter across. So if the universe is a billion meters across, an atom is a 10 billionth of a meter across. So an atom is, in a sense, the universe is big compared to the amount that an atom is small, so to speak. If you ask about a nucleus about 10 to the minus 15 meters across. So that's roughly a million billionth of a meter across. So we're kind of getting down to, we got a million billion versus a billion. So we're getting down to a slightly smaller level of smallness there. But so that's the size of a nucleus. Protons about the same size as a nucleus. Big nuclei are a bit bigger. Protons are depends on how you sort of count the size of the proton, because it's kind of a bit of a fuzzy thing. But then you might ask, well, what's even smaller than a proton? And what do we even know about what happens on sizes smaller than a proton? Well, we can use particle accelerators to kind of probe. They're kind of like giant microscopes that can be used to kind of probe what happens at shorter distances. So I actually happened to mention the phenomenon of diffraction, the phenomenon that when you sort of think light is going in a particular direction, it will always spread out a bit as a result of its wave nature. And diffraction actually limits the resolution of things like microscopes. So if you can't get to see with a microscope something that's smaller than the wavelength of the light or the whatever you're using to make that observation, it's sort of obvious that that would be the case, because in a sense, if what you're detecting is the peaks and troughs of that wave, and you have a thing that's smaller than the distance between those peaks and troughs, it's like it's not going to have any effect on the peaks and troughs, and so you don't get to notice it. So that's if you're using visible light, for example, which has a wavelength 500 nanometers. That's about well, it's large compared to the size of an atom, which is like a tenth of a nanometer. And so visible light, you can't make a visible light microscope that will see individual atoms. They're too small relative to this big sort of fat-fingered kind of light that is trying to probe them. If you want to see atoms, you have to have something where the wavelength of the thing you're using to see them is smaller than the size of atoms. And for example, in X-ray crystallography, you can effectively see positions of atoms by using X-rays, which have shorter wavelength. And the way that X-rays are reflected from crystals depends on the way that the atoms are lined up in the crystals, but it needs a wavelength that is comparable to the distance between the atoms. So in any case, generally you need kind of higher energy particles, shorter wavelength particles to be able to kind of probe shorter distances. And particle accelerators are sort of an extreme version of that, producing particles of very high energy and therefore very small wavelength. And so the smallest distances that have been probed with particle accelerators directly are around 10 to the minus 20 meters. So that's whatever it is, roughly a hundredth of a billionth of a meter. So again, the big side is billion, billion, billion. Even that small side is about billion, billion. So we're off by a factor of a billion there on the small side. So what happens even below the scale that particle accelerators can see? Well, one question that comes up is, what about electrons? How big is an electron? Well, in usual theories that have existed, an electron is infinitely small. Now, there are features of electrons where there are kind of is a whole cloud of photons around it and so on, and that big fluffy thing is bigger than that. But the core electron is effectively of zero size in the traditional theories of particle physics. In our models so that's kind of so far as people have known, electrons are of zero size. Now, as you go down to sort of smaller and smaller distances, things start to happen. For example, the effects of quantum mechanics start to be important, and the effects of quantum mechanics even start to be important on the structure of space. And there's a distance, the Planck length, about 10 to the minus 34 meters, which at which the quantum effects on the structure of space necessarily become important. We usually think of space as nice and uniform and consistent, but when we're dealing with sort of quantum mechanical space, it necessarily becomes a very kind of a place where lots of variation is happening all the time. So that's the Planck length, 10 to the minus 34 meters, is sort of more on the small side than the 10 to the 26 meters is on the big side when you look at the whole universe. In our models of physics, there is structure in space at distances quite small compared to the Planck length, perhaps as small as 10 to the minus 100 meters. And in our models, space is actually made of this kind of network of discrete elements. We can think of them as atoms of space. There really isn't, there's nothing in between. It's just space is this network of atoms of space. And the effective distance between those atoms of space, even though there's no ambient space in which we can talk about distance, but when we line up enough atoms of space and their connections, we could sort of deduce that the effective distance between atoms of space maybe is around 10 to the minus 100 meters. So in that picture, going down to the smallest, one would be going down a lot further than one has to go up to get to the whole size of the universe from us. From our 1 meter scale size up to the whole size of the universe is less than going down to the elementary length. So it's an interesting question whether what structure might exist in the universe on very small scales. We know on very large scales, we have galaxies, we have clusters of galaxies, all those kinds of things. On the small scale, we know we have particles like protons and so on. We have electrons. We don't know how big those are in our models of physics. They have to have a definite size. In fact, my guess is that they are as big as 10 to the 30th elementary lengths. But 10 to the 30th elementary lengths is 10 to the minus 70 meters. So absolutely tiny compared to, for example, the size of a proton. But that's some kind of sense. But what happens at these very, very, very small scales and how much structure there is there, we just don't really know. And that would be, so it is interesting that we exist at this size that is sort of intermediate between the size of the universe and the size of the smallest things in the universe. And probably our experience of the universe critically depends on that sort of scale size of us relative to biggest and smallest, so to speak. But interesting question. Okay, let's see. Okay, so RBS is asking, when will we reach the physical computer chip size limit? They say, I heard in 2 or 3 years. Okay, so what is a computer chip made of? A computer chip starts with a very pure silicon crystal. So it's basically, silicon is one of the main ingredients of rock. Silicon and aluminum are the sort of main typical ingredients of rock. Actually, silicon is the number one ingredient. With great effort, silicon is purified and turned into perfect crystals. Perfect enough that there are very few atoms out of place in a big wafer of silicon. And you get the atoms are all lined up in this very particular array that silicon crystals put atoms into. And then what happens when you make a microprocessor, for example, is that you are etching out little channels that sort of serve as wires out of that silicon, and you're doping them with atoms of other materials that have different numbers of electrons associated with them and so on. And so the big issue in getting the big sort of figure of merit in making microprocessors is the feature size, essentially how big those wires can be. And so sort of 3 nanometer wire sizes is kind of a sort of the high end of what's achieved today. And that means, so the actual silicon atoms might be 1/10 of a nanometer across. So that means we're talking about 30 atoms across the width of a wire. And the question is, how do you etch something at that size? Well, the wavelength of light is might be 500 nanometers. It's way too big to be able to etch something of that size. And so you can't use visible light. In the early days when microprocessors were made, well, what was typically used was ultraviolet light, which has slightly shorter wavelength. But the thing that's been done in more recent times is to use X-rays and electron beams and other things that have shorter and shorter wavelength so that they can successfully etch out those very, very tiny wires. And there's not really a limit to how far you can go with that. You just have to have higher energy particles. Of course, you're going to reach the point where the wires are comparable in width to the distance between silicon atoms, and then you're really stuck. You can't go beyond that. But there are many. Why does it matter how wide the wires are? So one reason it matters is because you want to pack more and more components. So roughly a transistor, which is sort of the key ingredient of circuits, it acts as a switch. A transistor is roughly made by crossing two wires. It's not quite that, but roughly what happens is there's usually in a so-called field effect transistor, there's usually sort of current flowing from the source side to the drain side. That's sort of one wire. And then there's a wire that goes across. That's the so-called gate wire. And when you put a voltage on that gate wire, you can prevent current from flowing the other way. And so that provides a switch. And by making just a very small change of that voltage, you can have a big effect on the current. And so that can be used to amplify things. But when you're making a modern microprocessor, you might have a billion of those little wire crossings that make these components. And you want those wire crossings to be, you want to pack as many of them as possible into a small region for many reasons. Probably the most important ultimate reason is capacitance. Basically, how many electrons you really have to schlep around to to send a signal, to change the signal you're sending through the wires. If there's a really big sort of clump of electrons there, then it's just more effort and it takes longer, and the speed of the microprocessor will be slower. But so that, and there are also effects, like if you make two wires be too close to each other, you'll have sort of the electrons going through one wire will affect the electrons going through the other wire, and so on. But in general, you just want to pack in more wires, more transistors, and so on. And that's also important, that the capacitance effect is also important in terms of the heat dissipation that you get, and so on. You know, you can't run your microprocessor so hot that it melts the silicon, for example, or even so hot that the electrons and the dopant atoms in the silicon kind of start moving around. Then your microprocessor will no longer work. But this question about how do you pack in more components? Well, one of the things that tends to happen right now is that a microprocessor is made in many layers. I don't know how many layers it is these days. I'm going to make a wild guess of 20, but I'm not sure that's right. But you're making these layers, but fundamentally things are in two dimensions. The wires are mostly going just in a plane. Maybe there'll be one that goes up a bit and so on. But people have talked for 40 years at least about making truly three-dimensional microprocessors, where there really are wires going sort of equally well in the up-down direction as in the sort of flat direction. That hasn't happened yet, and I think there's just a lot of technical difficulties in making that work, and a lot of kind of precision manufacturing issues in making that work. But I think those are some of the constraints. Now, you know, in terms of how do you deal with sort of getting very small wires, very small numbers of electrons, there will be limitations. For example, right now, a single bit in a typical memory chip, for example, or microprocessor is, I think, around 100,000 electrons. And that's fine, because with 100,000 electrons, you can be pretty certain about, yep, we moved this 100,000 electrons here, and we moved them away from there, and so on. If you got down to 5 electrons, that would be much less obvious. It'd be much more like, well, did they really all move there? Yeah, a few of them kind of were stragglers and they got left behind, but maybe actually that bit was a 0, not a 1 type thing. And as soon as you're going down to the level of very small numbers of electrons, you have to start doing things like error correction, where you have many. That's already done in microprocessor chips, but it's already done in memory chips. It's not done in microprocessors. Nobody knows really how to do error correction for operations. They only know how to do error correction for something you're just statically storing in memory. Well, in any case, as you get down to too small a number of electrons, then yes, you'll have trouble just by being sure about what happened. And that's sort of one of the directions. I think, you know, one of the disappointments, I suppose, of microprocessors, there's just amazing amounts of engineering work and amazingly sophisticated engineering and physics that's gone into kind of gradually increasing the density of transistors on microprocessors and improving all sorts of different characteristics. But in the end, the clock speed, the rate at which you're kind of pulsing electrons through the circuit, hasn't really increased that much in quite a few years. It's in the a few billion, a few gigahertz, a few billion pulses per second, so to speak. And the whole so-called Moore's law of things double every 18 months hasn't really been true for quite a while. And it's sort of this idea of how much faster will computers get. A lot of the, oh, my computer is getting faster comes not from the individual pieces of circuitry getting faster, but the fact that you can have more pieces of circuitry running in parallel, for example, in GPUs, so that in effect, if your processing can be broken up into many things being done in parallel, like you're dealing with an image and you can deal with one part of the image in a separately from another part of the image, then you can effectively get a speed up, even though the individual processing of individual pieces didn't get any faster. And there's, I think, the notion that you can kind of, by improving the algorithms, by improving how parallel things can be, you can get lots of speed ups. That's been the story of the last quite a few years. So, let me see. Jürgen is asking, do you expect the propagation of light in your physics project? How do you expect it to work out? Will you get frequency-dependent propagation or not? Okay, so this is where things get a bit tricky. So light, as I mentioned, in a vacuum, the kind of simplest model for things is this very mathematically oriented, disembodied kind of electric and magnetic fields kind of idea. When light goes through a material, then what's happening is that it keeps on getting stopped by atoms. And then when it's stopped by an atom, it has to be re-emitted again to keep going. The photon is stopped, the photon is absorbed, the photon is re-emitted. Now, the issue is that absorption and re-emission takes a certain time. There's a certain, as the atom goes from one state to another after it's absorbing the photon, and it goes back down to the previous state again, that all takes a certain amount of time. And that means that light traveling in a material goes slower than light traveling through a vacuum. It's sort of tricky because in our models, this idea of, there is sort of a carrier, there is a thing in which the light is traveling, which in the kind of usual theory of so-called Maxwell's equations, it's just disembodied mathematics. But in a material, it's not disembodied mathematics. In a material, its atoms are absorbing photons and re-emitting them. And the question is, what's the delay? And some materials, that delay is longer than others. And the effect of that delay is to make light effectively go slower in the material than it does in free space. So for example, in water, light goes 1.33 times slower than it does in a vacuum, and it pretty much goes at the same speed in a vacuum as in air, because in air, it's just not hitting atoms very often. So it's not getting absorbed and re-emitted very often. But so in water, the delay, I should know the actual delay in femtoseconds or something. I don't. I could work it out. But there's a certain delay every time a photon is absorbed and re-emitted by an atom. In something like diamond, there's a longer delay. Diamond slows light down by a factor of 2.7. And that quantity is the so-called refractive index of the material. But what happens is that depending on the frequency of the photon, depending on the energy of the photon, the time it takes those atoms to re-emit the photons again, and in fact, it's mostly the re-emission, varies with the energy of the photon. So there are cases where there is so-called resonance absorption, where, there's really one question is, does it re-emit the atom, the photon again at all? Or does it just say, great, I got a photon. Now I'm a slightly higher energy atom, but I'm not going to spontaneously emit a photon again. And so that can happen, that the material effectively absorbs the photon and doesn't re-emit it at all. When a material is not transparent to visible light, that's what's happening. The photons are being absorbed but not re-emitted. When a material is transparent, what's happening is the photons are being absorbed and re-emitted again. And the the depending on the time delay, that will affect the refractive index. And in general, that time delay varies with the energy of the photon, and so that means the refractive index varies with, for example, the color of light. So, for example, that's how a prism works. A prism, you have, for example, white light comes in, which is a mixture of all different frequencies of photons, ones that are lower energy, like redder, and ones that are higher energy, like bluer. And what the prism is doing is in glass, the refractive index varies with frequency. And so which gets bent more? I think red light gets bent more. So I think that's right in glass that that there's some a that a photon that has lower energy, I think, is it's made to go proportionately slower in glass than a blue photon. And so that means when you have a prism which has that nice sort of prism shape, if you work out where if you work things out, you'll find that that causes the okay, as light enters a material that has a different refractive index, the direction in which the light travels changes. You can work that out pretty easily by looking at the wave fronts in the light, and as the speed of the light changes, the distance between wave fronts changes because the light has a fixed frequency. You're saying every, I don't know what it is, nanosecond, let's say, no, for light, every femtosecond, there's another sort of peak in the electromagnetic wave. That's the frequency of the light. The wavelength is the distance between those peaks. And that distance is related to the frequency by the speed at which the wave is going. So if the speed the wave's going is the speed of light, you just have that the frequency is equal to the speed of light divided by the wavelength. But if the speed at which the thing goes changes, then that means the wavelength will get correspondingly longer and shorter with a fixed frequency. And when you work out the geometry, it means that when a sequence of wave fronts hit a thing with a higher refractive index, what happens is if those waves are coming at an angle that's far away from the kind of the normal direction, the direction sticking straight out of the material. Let's say you have a surface of water or glass or something and it's horizontal, and the normal direction sticks straight out of that. It's kind of the thing that's at right angles to the plane of the interface. Then if you have that pile of waves coming in at an angle, then what will happen is those waves will be, if the refractive index is larger, those waves will be turned to go more vertically. So it's as you get into that slower material, the waves go more vertically. So let's see. That was explaining. Yeah. So that's why in a prism you split red light and blue light because they have different refractive index. They go at different speeds. Therefore, they're bent less or more by refraction, and that means because of the shape of the prism that means that those beams of light will be split into the different colors. So in general, this phenomenon of when you're splitting light, it's called chromatic aberration. And most lenses made of glass, for example, have a certain amount of chromatic aberration. So when you look at things, you see actually, it's for some reason it's become more pronounced in recent years when you're looking at, car headlights coming at you. And this also happens as eyes get older, but I don't think it's as a result of my eyes getting older that the effect is larger. I think it's because of halogen and LED lights. But in any case, you'll see these kind of rings of different colors, for example. And by the way, that same effect is what leads to rainbows. It's in the water drops that sunlight is being refracted and reflected through. The angle depends on the frequency of the light, and so the red light and blue light have different frequencies, and so they come out at different angles. Okay, so there are materials that are so-called dispersive. They have a refractive index that changes with frequency, and there's others that do not. As far as we know, the vacuum is not a dispersive medium. As far as we know, the speed of light is the speed of light for all frequencies of light going through a vacuum. So the question is, in our physics project, is that true for all frequencies or not? And my guess would be when the frequencies are outrageously high, comparable to so that the wavelength would be comparable to the elementary length, the effective distance between the atoms of space, then all bets are off. Then the speed of that propagation, the speed of that at which those waves will go through the medium, so to speak, will be dramatically different. Away from that, I would not expect much difference. The one thing that is different in our models is that space is not necessarily precisely three-dimensional. There are dimension fluctuations, places where space might be 3.01 dimensional or 2.99 dimensional. And that has presumably a dramatic effect on the propagation of light through those regions. You might remember I was talking about the inverse square law as this thing that determines kind of how much of, well, gravity, or actually also electromagnetic waves that start from a point you'll get at a certain distance. How much you'll get depends on the dimension of the space. So if you're in 3.01 dimensional space, then the amount of that you get at radius r will go like r to the 1 over r to the 2.01, not 1 over r to the 2, i.e. 1 over r squared. So my guess is that there are probably some very interesting effects from dimension fluctuations. We don't know how many dimension fluctuations might have been left over from the early universe. And I have to say, I am sort of frustrated that I still don't know exactly what happens to an electromagnetic wave propagating through a dimension fluctuation. I've been kind of hoping that somebody else will figure that out. And I'm kind of, I haven't worked out something. Is that true? I'm going to say I haven't worked out something in classical electrodynamics like that for many decades, but I think that might not be true. I think I might have figured things out. Yeah, I think I have actually. But that particular thing, I feel like I have to I have to kind of retool a bunch of things from classical electromagnetism to try and deal with fractional dimensional space, which they've never been set up to deal with. So there will be effects like that. For gravitational waves, one of the things that seems to be true is that gravitational waves that come from the deformation of masses, just like electromagnetic waves come from moving around electric charges, gravitational waves come from moving around masses. Gravitational waves are really hard to detect, and mostly we only get to see them from incredibly violent events. Like we've gotten to see, well, probably once a week now, the mergers of black holes somewhere in the universe. They produce huge amounts of gravitational radiation. They'll take in 1 second, they'll convert the mass of the sun, the equivalent of the mass of the sun, into pure gravitational radiation. And if that happens anywhere in the universe, gravitational wave detectors can now detect that, more or less. And the question is, those gravitational waves that were produced in that 1 second of the merger of black holes, do those gravitational waves, how fast do those gravitational waves go? And the answer is, they seem to go at the speed of light. But in our models, my guess is that there will be deviations from that. And that I just don't know what, I mean, it's a complicated piece of physics to work out, even given our models, what the effect on a large gravitational wave would be, because our models are dealing with what happens at the scale of sort of very elementary pieces of space, yet a gravitational wave involves, 10 to the 100 different atoms of space. And you have to kind of see what the collective effect of that is on the gravitational wave. So uh, let's see. Oh, there's one question here from Greg. If light has no mass, how can gravity, like from a black hole, pull it in? Um, okay, the reason that happens is that the how best to say this? Um, the way that one thinks about gravity in, well, ever since general relativity was invented in 1915, is that gravity has to do with the curvature of space. So what does that mean? Well, normally, let's say that things, whether they're photons, electrons, anything that doesn't have forces acting on it, will just go in a straight line. Well, what is a straight line? Actually, we don't say it really goes in a straight line. We say it goes in the path that takes it, in which it has to go the minimum distance to get from one point to another. It doesn't just sort of wander around. It always just goes the minimum distance to get from one point to another. So in ordinary flat space, the minimum distance between 2 points is a straight line. That's not true if the space is curved. If you're on the surface of a sphere, like on the Earth, for example, the minimum distance between 2 points is a great circle path on the surface of the sphere. And the idea is that in the structure of space-time, that one can think of space as being curved. And sort of the big idea of general relativity is that the presence of mass produces curvature in space. And so these particles, they still think that they're going the shortest distance. They're going on the shortest paths, so-called geodesic paths. But those shortest paths, when space is deformed, those shortest paths are no longer straight. And in particular, the shortest paths are exactly the paths that you follow if you were to say, well, it's being deflected by gravity. So we don't really have to talk about gravity. We can just talk about the fact that things follow their shortest paths, but the shortest path is deformed by the presence of mass making space be curved. So that's what's happening to photons, for example, when photons, for example, a bent light is bent when it goes around the sun. In fact, that's even true without general relativity, but you get double the bending with general relativity when light goes around the sun. That was something that was, well, supposedly detected in 1919, although that experiment may have been a bit of a fudge. But it's certainly well known by now that this deflection, you can think about, it's the result of it still going in the shortest path, and it's going in the shortest path, but consistent with this deformation of space. I mean, the thing that happens is when something is going fast enough, it will be able to escape the gravity of a thing. So, for example, for the Earth, if you shoot something up in the air faster than 25,000 miles an hour, it will have enough momentum that it will escape the gravity of the Earth. It will not, the amount that the gravity of the Earth is pulling it back and slowing it down will not be sufficient to overcome the inertia it already has, and it will escape from the gravity of the Earth. For the sun, the number is 100,000 miles an hour. For the galaxy, it's 1,000,000 miles an hour. But in any case, there's this question of how fast you have to be going to escape the gravity of a thing. And the question is, well, is there something where it has so much gravity that even if you're going at the speed of light, you can't escape the gravity of the thing? And that's what black holes are. They're things where the escape velocity, how fast you'd have to be going to escape the gravity of the thing, is the speed of light. And what forms that's basically what's happening. And I mean, in the most extreme case, photons can actually orbit black holes. So just as now normally with the Earth, a photon absolutely wouldn't orbit the Earth because the speed of light is um, uh, is 186,000 miles per second, and the escape velocity of the Earth is 25,000 miles per hour. So light is way faster than the escape velocity of the Earth. So it just zips right past Earth without getting sort of captured by the Earth, without getting preventing it from escaping. But around a black hole, light can get sort of pulled into the black hole. But if you arrange the light just like if you just dropped something from high above the Earth, it would just fall to the Earth. But if it is traveling at a certain speed relative to the Earth, it can be in orbit around the Earth. When a spacecraft is sent up, it goes up for a while and then it's kicked sideways to insert it into an orbit around the Earth. And the uh, that's well, it's complicated because the Earth is spinning and things like this. But in any case, the thing that can happen with a black hole is normally that photon that's just coming towards the black hole will be just pulled into the black hole. But if the photon is going at just the right angle, the photon can end up being in orbit around the black hole. And that's what there's maybe actually has been observed, kind of photons in orbit around black holes, around the central black hole of our galaxy. And that's kind of an effect that comes about where you can have where you can have that phenomenon of the photon gets trapped in the orbit, but it's still sort of going. It's not falling all the way into the black hole. It gets trickier when there are black holes that behave as if they're spinning, and all sorts of fun things happen there. But it looks like I have to go back to my day job here. So I think we should wrap up for today. I see all sorts of other questions here, which I would be happy to try to address. I will say that I've been trying to think about sort of how I should be organizing these live streams. I currently have 4 series of live streams. This science and technology Q&A for kids and others. I have a Q&A about history of science and technology, Q&A about future of science and technology, and Q&A about business, innovation, and managing life. And I've been doing that particular set for must be a couple of years now. And I think they work pretty well. Some things that I've not been doing are things where I'm actually showing kind of live computational things and actually seeing results come up live. I've done that a few times. I did a kind of math storytelling day fairly recently along those lines. But I've been wondering whether I should mix in some of those things that where you can sort of actually see things happening on the screen with these more sort of audio first kinds of things. I'm also wondering if I should do some slightly more technical discussions. I mean, I make every effort here to be able to explain whatever I need to explain at a level that people I hope will understand. But for example, that if I was explaining that question about wave-particle duality, if I were allowing myself to use a little bit more mathematics and so on, and talk about differential equations and all kinds of things like this, I will have a different kind of explanation that I can give. So I am interested in people's input on what they would like to see. Yes, I see there's people commenting that it's fun to see me in my natural computational habitat. Yeah. Okay. All right. We have some comments, some encouraging actual do it with live computation. I have to say, I feel like it is more intense for me to do that because I don't want to be too boring and end up with, oh, this code just doesn't work. There's a bug. I'm trying to find this bug. And it's 10 minutes of messing around and looking at things and trying things. And oh my gosh, that's still not working, et cetera, et cetera, et cetera. But I think technological help is on its way. And in fact, some things that we've been working on very recently, which hopefully will be announced fairly soon, may make it a great deal easier to do that kind of interactive debugging and to get started on things and not have to say, oh, I need to go and read the documentation on that and so on. So, okay, well, uh, okay, but I'm seeing a lot of positive feedback for this idea. All right, I will then I will try to do that. All right, well, I should run off now, but thanks so much for joining me, and look forward to talking to you another time. Bye for now.